find the derivative of a quotient of functions, we first plug it into the limit definition of the derivative. Just starting off with this, it looks a little crazy or messy or confusing. So the first step I would like to do is get only one fraction, and I'm going to do that by multiplying the top and the bottom by the LCD. What is the LCD? You have g of x plus delta x, g of x, and the denominator of the denominator is just 1. So our LCD is going to be g of x times g of x plus delta x. We're going to multiply this by g of x times g of x plus delta x over g of x times g of x plus delta x. If it helps you, you could also say this is over 1 and this is over 1. Either way, you're multiplying by a special form of the number 1. So now we have the limit as delta x approaches 0 of this distributed into this. The very first fraction will have this as its numerator and f of x plus delta x, so it'll be g of x times g of x plus delta x times f of x plus delta x over g of x plus delta x minus f of x times g of x plus delta x over g of x, this denominator, over numerator times numerator, denominator times denominator, so that would be delta x times g of x times g of x plus delta x. G of x plus delta x over g of x plus delta x is 1. G of x over g of x is 1. So take those out of the fractions in the numerator for our next step. And by doing that, we no longer have fractions in the numerator. All right, but we still don't have stuff that we necessarily know yet. At this point, we're going to do something similar to what we did in the product rule proof, in that we're going to add and subtract some quantity in order to rearrange this to things that I am more familiar with. So what happens is we're going to subtract f of x times g of x, and if we subtract some random product, we also need to add it. We're still subtracting f of x times g of x plus delta x, and it's still all over this denominator. You may be able to somewhat recognize limit definitions in here, like f of x plus delta x minus f of x, and both of these terms are being multiplied by g of x. So let's factor out the g of x, and you have f of x plus delta x minus f of x. Okay, that is the numerator for the limit definition of the derivative of f. And then we also have, if you'll notice, you have g of x plus delta x and g of x. Now the signs are a little bit different than what they should be. So when we factor out an f of x, we want the minus to be in front of the g of x, so we're going to factor out a negative f of x. In this step, I'm going to rearrange the terms in my head. So divide negative f of x from this term, and you get g of x plus delta x. And then divide negative f of x from this term, and you get negative g of x, which is the numerator for the limit definition of the derivative of g of x. But still, these are just the numerators, and we have some kind of strange looking denominator going on. What I would like is to have this be the numerator of a fraction with delta x in the bottom, and this be a numerator of a fraction with delta x in the bottom. Then I could perhaps substitute in derivative of f or derivative of g. My next step is to get this delta x into the numerator. Get rid of it down here in the denominator. So I'm going to multiply by 1 over delta x. If I multiply 1 over delta x times the denominator, will it go away? Yes, it will. So 1 over delta x over 1 over delta x will be what I multiply by. So now that we just got the fractions in a couple steps ago out of the numerator, we're basically putting them back into the numerator. We have g of x multiplied by f of x plus delta x minus f of x over delta x. The g of x is being multiplied, so you can extend the fraction bar, or you don't have to. Minus f of x. Take that out, and you have g of x plus delta x minus g of x. This is being multiplied by 1 over delta x, so now this has a denominator of delta x. And again, the f of x can be in the fraction bar, or you can leave it in front because it's being multiplied. Now, when you multiply the denominator by 1 over delta x, that becomes 1, and 1 times g of x times g of x plus delta x. Now I'm getting to a place where I might actually be able to fill in some of these definitions. So at this point, I'm going to split the limit to be the limit of the first fraction minus the limit of the second fraction over the limit of the denominator, because algebraic properties of limits. I'm going to take several things out of the limit that do not involve delta x, such as this g of x will go in front of this limit, this f of x will go in front of this limit, and this g of x will go in front of this limit to help us simplify further. Okay. Let's substitute our definitions of the derivative. So I have g of x times this, which is f prime of x. Minus f of x times this, which is g prime of x. G prime of x, all over, when you substitute 0 in for delta x in the denominator, you get g of x times g of x plus 0. Well, g of x plus 0 is just g of x, right? The derivative of a quotient is the lower function times the derivative of the upper function minus the upper function times the derivative of the lower function over the lower function times itself, which is called squared. This is the quotient rule. Woo! how are we going to remember this? You don't have to remember where f or g are in the fraction, because we're going to use the words low to talk about the denominator and high to talk about the numerator. So f of x would be the high function, the one in the numerator, and g of x would be the low function, the one in the denominator. So the saying goes, low d high minus high d low, derivative of the lower function, over low squared, we go. Low d high minus high d low over low squared, we go. Low d high minus high d low over low squared, we go. Low d high minus high d low over low squared, we go. Over low squared, we go. Low d high minus high d low over low squared, we go. Over low squared, we go. Low d high minus high d low over low squared, we go. Let's try it out. Low d high minus high d low over low squared, we go. This is my lower function, this is my higher function. That's not necessary to label, but I just want you to know what we're talking about. So y prime is equal to the fraction low derivative of the high, low d high, minus high d low, high derivative of low, x squared plus 1, over low squared we go, x squared plus 1 squared. Okay, we are going to find the derivative of these and then do some algebra to simplify. X squared plus 1 is being multiplied by the derivative of 5x minus 2. Okay, remember the derivative of a line is just its slope. What is the slope of that line? 5. Minus the quantity 5x minus 2 times the derivative of x squared plus 1. Pop down, power down. Pop the 2 down and you will get 2x to the 2 minus 1, which is 1, plus derivative of 1 is 0, derivative of any constant is 0. Over low squared we go, over low squared we go. Expand the numerator and combine any like terms possible. We have 2 like terms, the squareds, combine those and we're done. It's not very common that in the quotient rule you would actually square that denominator and expand it out, okay? Usually expanding a denominator is just not going to simplify very easily, so we leave it as low squared. That one is a very easy example of the quotient rule, very straightforward. Let's try some more. The denominator is root x minus 1 and the numerator is x. Sometimes it's helpful to rewrite the roots, so this quantity can be rewritten as x to the power of 1/2 minus 1. The derivative, or h prime of x, would be the quotient rule. Low d high minus high d low, over low squared we go. Low d high minus high d low, over low squared we go. H prime of x. x to the 1/2 minus 1 times the derivative of x. The derivative of x is 1. Minus x times the derivative of x to the 1/2 minus 1. Pop down, power down. So you have 1/2 times x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. Derivative of a constant is 0. So continuing on, we have x to the 1/2, distribute this 1, and then multiply these two. So x to the 1/2 minus 1 minus, we're multiplying, okay, a negative 1 times a 1/2, so that's a negative 1/2. And then you're multiplying an x to the 1/2 times an x to the negative 1/2. x to the 1 times x to the negative 1/2. Remember, when you multiply the same base, you add the exponents. So 1 plus negative 1/2 is positive 1/2. That ends up being a positive exponent. There are some like terms. There's an x to the 1/2 and an x to the 1/2 that we can combine. So you have 1x to the 1/2 minus 1/2 x to the 1/2 leaves me with 1/2 x to the 1/2 minus 1 all over x to the 1/2 minus 1 squared. The struggle with calculus sometimes is like knowing when to stop simplifying. Like, when am I done? You know, up until this point, people told you that radicals in the denominator were absolutely not okay, people, aka me. And in calculus, we just kind of don't care as much, okay? And I've researched this. It's just, at some point, you can just keep simplifying and simplifying and simplifying and writing in a different form and a different form. So radicals are okay for us to leave in the denominator for these assignments. But if you have fractions, let's try to get them to be one fraction, okay, rather than multiple fractions with multiple denominators or weird things. Right now I have a 1/2 that's in this numerator, so I'm going to factor that out in the numerator. So 1/2, just because I want this 1/2 to be not a fraction in the top. 1/2 times x to the 1/2 minus, and then 1 divided by 1/2. That's what you're doing when you're factoring. 1 divided by 1/2 is 1 times 2. And then you can check by distributing back in 1/2 times -2. Does that give you -1? Yes, it does. All over x to the 1/2 minus 1 squared. So now I can take this 1/2 and multiply it by the entire fraction now that I have factored it out of the numerator. H prime of x is equal to x to the 1/2 minus 2 over 2 times the quantity x to the 1/2 minus 1 squared. I would like your answer in radicals rather than fractional exponents. So h prime of x is equal to root x minus 2 over 2 times root x minus 1 squared. So yes, there is a root in the denominator, but we have one fraction. It's pretty consolidated, and so we're going to stop it there. I wanted to include some other types of problems that you may see and how you can approach them. In this, you may think that we would want to write 1 over x as x to the -1, but that can get complicated to have a negative exponent and a fraction already from the get-go. So the book suggests that we get only one fraction rather than a complex fraction. So multiply by the LCD. This is over 1, this is over 1. So the only little denominator we have is this x. We're going to multiply the top by x and the bottom by x. You can even tell yourself it's x over 1 over x over 1. So f of x could be written as 3 times x minus 1 over x times x is 1. And we're distributing again, so x times x is x squared. X times 5 is 5x. And at this point, then you could use the quotient rule and it would be a lot easier.